Okay, so dahil na sa tuwang discussion. So natay added ng mga limitation here. So we have here the critical damping ratio and then the critical damping CC. So here the critical damping ratio actually this is our decay function. It will show us kung unsa kapaspas mo dump ang usa ka structure. So di ba sa usa ka structure pwede siya nga taud-taud iyang pag-dump diretso na medyo paspas ang pag-dump naapoy structure nga sabi kay kadako og dumping and etc. So this one here, this critical damping ratio is our decay function because it will show us the behavior of dumping sa ato ang structure. So let's move on sa ato ang equation, sa ato ang discussion rather. So this is just a continuation, no? So if we go back sa ato ang first principle dito that ut is equal to g1 es1t plus g2 e to the s2t. So that is from our first principle that the solution of u of t is equal to g e to t. And our s here, we have two solution for the s. No, we have a positive and a negative. We just apply this concept here. So this is our first condition, and we apply the value of the s, which is this one. And then by the loss of the exponents, no, di ba ang katong gingon nato nga e to the a times e to e to the a plus b. So ang kanila siya nga concept is ato siya gipaatras, no? Na from this point ato siyang gihimuon ingani. So so we have a common here, no, natin mga common factors, this one. So ato pa that equation mura siya gayong g1 e to the negative xi omega t times e to the I omega d t plus g2 to the negative xi omega t times e to the I omega d t. So if you notice no natin duha ka omega, we have the natural frequency and then the damp natural frequency or natural frequency. So we can factor out these common terms on these both functions, and then we will come up with this equation 18. So same niya po sa to ang underdamped na system or no as a general solution sa to ang differential equation. Di ba, if we have a general solution para makuha silang constants, let's say we have our arbitrary constants here, g1 and g2, para makuha na, we try to get our u0 and then the u dot 0. So after ni mo ni makuha si u0 and u dot 0, you try to solve it algebraically, no, by elimination or depending sa imong style kung sa mas dalian nimo. And eventually, our new equation of motion or for the lateral displacement will look like this. U of t is equal to e to the negative xi omega t times the quantity, we have here the response velocity plus the lateral displacement times xi omega all over omega d or the damping natural frequency times sine omega d t plus the lateral displacement times cosine omega d t. So if you notice now after these initial conditions and then you apply again the Taylor series, say I omega d t in this function, and then you will arrive with this equation. So kung yung tanawon, we have the sine and the cosine. So expected yapon na ang graph na to will to be sinusoidal. But here there is some percent of dumping. So eventually makita na ginato sa graph that the graph will certainly rest. It means that the structure will certainly stop oscillating or will stop moving. And then finally no those that equation ato pag gina siyang ma-summarize in this formula. Same with the same with the undamped system. So this one we call this underdamped. Underdamped is different from the undamped. Undamped is there is no damping. Underdamped it means that its damping is less than the damping coefficient is less than the critical damping 2m omega. So we can simplify the equation into this one. So di na natin show kay taas tayo. And then we will have our formula for the amplitude rho, which is equal to this one. So there is already a damping ratio, and then also the omega natural frequency, and then the damping natural frequency involved with this one. Sa to ang equation. So this is just a, actually we can derive that one, pero medyo taas naman nga time ang makonsume. So we just showed the summary of that one. So lain na siya ang pamagi pag-solve sa to ang amplitude. And then our angle no of our tangent is this one na dayon for the underdamped system. So the equation 20 says that the underdamped system in its free vibration stage will oscillate with circular frequency omega d and will exponentially decrease amplitude. So we have here an exponential function pasabot its decay or its Bato siya no ang iyang pagka-decrease sa iyang amplitude is there is an decrease exponentially. So mo siya ang system sa tuwang underdamped system. So again, this is free vibration. There is no consideration for a added dynamic force. And then the structure or the SDF system is oscillating with a circular frequency omega d. Again, if you remember omega d, just equal to the omega times the square root of 1 minus xi squared or the critical damping ratio squared. Usually, no, the critical damping ratio is gamay na siya, that is less than 15 or 10%. And then in very flexible structure, that is around 1% or 2% ra gid. So gamay na jud kayo. So since gamay ra mo jud kay na, square pag gid mo mosamot sa kagamay, so more likely ang ato ang omega d here is almost or approximately equal ni omega, because the omega d will have a value of like 0.998 so there is actually difference of the 1, but that is approximate to the value of the omega, approximately lang. So in this system, realistically, so before no, we try to analyze the structure na undamped, that is not an realistic behavior. Now, this is a realistic behavior na when the structure will be oscillating and then it will eventually come to a time or to a point where the structure will stop oscillating because of the application of the damping. So here now we have a graph of the time versus displacement again, similar with the previous that we showed. But so all of them so for kuano for compact for para sa ma-compare nato sila, we have our U0 here, nagsugod sila. But if you notice no, we have a undamped free vibration here. So the undamped free vibration or structure, its oscillation is equal. And we know that that is not realistic. And then the underdamped structure is, kung yung makita no, na a significant difference in its amplitude. Nagtagamay siya until it will come to a gamay na rin kaya, it will eventually come to a stop. Now, its decay, so mo, again na, mo yung pag-decay, mo na siya ang undang ni structure, no? It will stop oscillating. So its decay, it's the decay of its amplitude. So kung nyo makita, that is exponentially. there's a equation that is exponential. There is an exponential decay as shown by this one. Mo yung gingon sa inyo nga katong decay function nga si xi. So mo yung behavior, and then eventually it will come to a stop. So here, as you can see, we have natural period t, and then we have the natural period and with damping. So as the damping is already considered with this. So kinyong tanawan no, there is a delay in the position of the natural period to complete one cycle when damping is already applied sa tuang infrastructure. Okay, moving on. So we have here now, we try to see the effects of damping on free vibration. So yun nga, in most structure, we have here, the critical damping ratio is less than 0.2 and hence omega d is equal to omega and Td or the natural period due to damping is equal to T. So again, no, the critical damping ratio that is equal to C over the critical damping coefficient. Since that is less than 2, muna siyang nasa ingani. Omega d is approximately equal to omega and then the natural period due to damping is approximately equal to the natural period. So for example, no, our damping ratio is 0.2. So gamay na lang jud kayo. And we know that diba C is equal to critical damping coefficient times the xi. So we have m omega 0.2 or so our damping will become 0.4 m omega. And if we try to solve or to get the natural frequency due to damping, we have omega d is equal to omega times 1 minus xi squared. So let's see if our damping is 0.2, our coefficient damping, we have 1 minus 0.2 squared. So we have omega squared of 1 minus, so our 0.2 squared is equal to 0.04. So that is already equal to square root of 0.96 or the square root of 96 is 0.9797996 omega. So kung yung tanawon, si omega dako is equal to 0.9797996 omega for xi equal or less than sa 0.2. So kung yung tanawon, that is approximately omega d, kung round off ninyo, equal to 1.0 omega. So hence, since our omega d is approximately equal to the natural frequency when the damping ratio is very small, therefore its natural period also, since our natural period is equal to Td is equal to 2 pi over omega d, since doon kayo si omega d approximately equal to omega, then mo siya nga approximately equal po si damping natural period na to with the natural period of the structure. So here now we have a graph. So here now, this is a graph of the ratio of the natural damping, damped natural frequency over the undamped natural frequency versus the damping ratio xi. So when our damping ratio is 1, its natural, the ratio of the damped natural frequency over the undamped natural frequency is 0 or almost equal to 0. So muna siya ang katong frequency niya is in harmony, sorry, not that one. Muna siyang pasabot nga at damping coefficient na approximately equal to, no, the damping coefficient C over the critical damping is almost equal. Since almost equal sila, no, that the moment that the structure, there is an applied force on the structure or in its free vibration, the structure will, actually, there is almost no frequency. So, may nga ang frequency, si structure na siya yung graph. No, kasi sayo siya. But when there is no frequency, the moment that there is to a stop, eventually through time. And the more we move, the more that the damping ratio is gamay. So since common damping ratio man sa structure is 0.2 and below, mo na siya makita din nato nga mag-increase ang ratio nilang frequency, damped natural frequency, and the undamped natural frequency. So mo na din itong mga-increase ang there's an oscillations or cycle that will happen on the structure. So mo na din siya nga almost, so ang connection na nila almost similar. Silang omega d over, kung yung makuha no, ang 2 points nila is almost equal, almost same, omega d over omega, and the damping ratio coefficient. So, muna siya. So, let's move. So, here now we have the another graph again. So, on the x-axis, this is the time over the natural vibration period. And then we have on the y-axis the displacement at time over initial displacement. So nagay duha ka graph diri. Kung niyo makita, we have graph 1, graph 2, graph 3, and graph 4. Si graph 1, si curve 1, it has a damping ratio xi equal to 0. So pasabot, there is no damping. This is harmonic oscillation. So katong undamped system. So this undamped system kani si curve 1 maintains its motion. It maintains its frequency throughout time. Now 2, 3, 4 has differing damping coefficient or damping ratio. So we have 1%, 2%, and 5%. So that is 0.01, 0.02, and 0.05. So you ma-notice no ang difference when there is 1% damping. So kani siya, this second curve here. And then the third curve here, it has 2% damping ratio. And then this one here, kani pinakasunod, it has a damping ratio of 0.05. So the more na magka-increase the IC damping, the more the energy that is being released, pasabot, the more that the structure will return to its original or neutral position in a shorter period of time. So we have here the damping in structures. These are common or general values. In seismic design of most structures, damping ratio is equal to 0.05 is used. So gamay result kila siya, no? And for tall buildings subjected to strong winds, we generally assume that it has a damping of 0.05 to 0.005 to 0.02. So this is from 0.5% to 2%. Here we have a 5%. And for single cables, that is 0.03% to 1%. So here now on the other side, we have our general or typical damping ratios. For a flexible frame, steel frame, ang steel frame that is flexible, no, that musayo, gina siya, mas musayo na siya kaysa ni concrete. It has a damping ratio nga 2%. So, gamay. And then for steel frame with dual tunnels, that is, it has a 5%. And eventually, magkadako siya, we have 1% here, 10% the other, and then we have a 5%. Pag abot din ni concrete frame with concrete or masonry shear walls, 10%. Concrete or masonry shear wall, 10% typical damping ratio, and wood frame and shear wall we have 15%. So sa to atong relation, if si xi, si damping ratio magkadako, pasabot ang time to return the structure to its neutral position is much lesser. So mas hinay, so iya ang but rather mas dali siya mo back sa iyang original position. Ang iyang oscillation mas magkagamay diretso through time. So muna siya. Okay, so again, no, so this is case 2B. So again, let's just recall now that we have three cases. A case 2, this is a case 2B. This is an underdamped vibration response. With underdamped when its coefficient of damping is less than to 2m omega. So in this section now, we have added the notation C xi, which is equal to the of critical damping. And then we have another S. So kada type or specific damping or cases, another S, another set or formula of equation na U of T, but same kapamaagi to solve the solution. We have the initial boundary conditions, and then we can try to solve it algebraically. Tapos applying the Euler's equation that is from the our numericals, if you remember that one, and eventually we will come up to another set of equation of motion for this under the free vibration response. So in our next discussion, we'll discuss the other two cases sa damp free vibration response sa tuang infrastructure.